Okay, let's come back to your textbook. We said the buffer is a weak acid and it's salt. This salt actually produces the conjugate base of this weak acid. We have some assumptions here. The first thing, because we have the weak acid dissociates partially to the H plus and A minus, but we assume that the amount of dissociation is very small, so most of the acid remains as HA in the molecular format. On the other hand, we have the salt. You know, the salts are soluble in water, and when they dissolve in the water, cation and anion separate from each other. So when you put this salt in the water, they produce cation and anion. The anion is actually conjugate base of this acid. And we assume that all of the Ma, all of the salt dissociates to the cation and anion. So the concentration of the A minus or the anion is exactly the same as the concentration of a base. So let's move on to the next page. These two assumptions are mentioned here. So we assume that the HA which we have at equilibrium or in the buffer solution is same as the initial concentration of HA which we are adding there because it doesn't dissociate so much. And on the other hand, the concentration of the conjugate base is same as the concentration of the salt which we are adding to the solution because the salt completely dissociate to make the A minus. Okay, so the main component of the buffers are acid and its conjugate base, or we sometimes call it acid and the salt because the concentration of the salt and conjugate base are same. We have very famous equation, Henderson Hasselbalch equation, which can determine the pH of the buffer solution for us. It's very important, and the formula is given in the section 1 of the IB data booklet, so you don't need to memorize them. The pH of a buffer solution is equal to pKa plus logarithm concentration of the salt and acid. So if you have the pKa of the weak acid and you have the concentrations of the salt or conjugate base and the weak acid, you can find what is the pH of the buffer solution. For the basic buffer, you have this formula. POH equal pKb plus logarithm of the salt over base. Okay, the definition of POH is given here, but this formula is not available in the IB data booklet, but it's very similar to this one. So instead of pH here you have POH, instead of pKa here you have pK base, plus logarithm salt over acid here you have salt over base. But this formula gives you the POH. If you want to find the pH of this buffer solution, this formula works. 14 minus POH. Okay, so these two formulas are given here. Okay, let me explain a little bit about this buffer solution or basic buffer solution that we have. So we go back to here. So we said the buffer solution is weak acid and its conjugate base. You can make a buffer solution by weak base. So the buffer solution can be made by a weak base and its conjugate acid. A weak base, for example, is NH3. So if you have this one, its conjugate acid is NH4 plus. You know that the conjugate acid of a weak base has one more proton compared to the weak base. But again, this is the cation. You cannot have this one by its own in the solution. So it comes from the salt. So the salt that we can we can have here is NH4Cl. So if you have these two, this salt and this base, you have made a buffer solution, but the buffer is basic. So for this type of the buffer, the formula that we use is POH equals to PKB. PKB of what? Of this weak base that we have here, NH3 for example, is given in the IB data booklet, plus logarithm concentration of the salt. What is the salt? The concentration of this one, or this conjugate base, over the concentration of base.